Many thanks to the organizers for inviting me. I was really excited to get this invitation, given the presence of so many natural scientists and researchers of evolutionary computation in this workshop. My group has been interested in program synthesis for scientific discovery for some time now. And very recently, we have been exploring ways to use evolutionary algorithms in these problems. And I think that there's a tremendous amount to be gained by bringing together evolutionary algorithms and large language models and program synthesis in the context of scientific discovery. And in this talk, I'll try to make a case for why this is so. OK, so as mentioned, the setting here is AI for science. Our objective is to build AIs that can achieve superhuman performance at least some tasks in research in the natural sciences. So if you think about the overall picture of what the scientific process looks like, one can imagine a picture like this, that you start with a research question, then you generate some concrete hypotheses, you do some experimentation and collect data, you do some analysis on the basis of the data, and then you interpret, and then you report to the community, right? And there are back and forth loops between these processes and sometimes they need to be repeated many times potentially. OK, so for a concrete example, let's think about the heliocentric universe, right? So back in the day, we thought that all the planets moved around the Earth, but then there was this problem that there was this retrograde planetary motion, which meant the planets seemed to be moving backwards at certain points. And so there was this theory of heliocentric model that came to be proposed as a way of potentially explaining that. But then to actually validate that theory, there had to be some data collection. And so Tycho Brahe went ahead and collected a lot of data about the motion of the planet Mars. And then after this data was collected, he started fitting all sorts of curves to that data. Or Kepler started fitting all sorts of curves to that data. And then it was found that, OK, there is this kind of elliptical orbit that explains this. And then later, Newton started with that. And then we ended up getting the law of gravitation. And many years later, this whole process was repeated for general relativity and time dilation in Mercury and so on. OK, so this is the overall picture, the different processes of this scientific process. And we really want to bring in AI in all of those pieces. And at the very end of this talk, maybe we can have a discussion about how to bring in AI and specifically program synthesis, evolution, and so on in addressing all of the parts of this puzzle. But today, we'll specifically talk about one part of this for the most part, which is the problem of analysis. So you're given scientific data, and then you are trying to come up with hypotheses that explain that data, right? So for example, that equation over here. OK, so then the problem that we are going to focus on is this problem that's known as symbolic regression in certain parts of the world. But to me, it's just a form of program synthesis. You're given a bunch of data, and you're trying to extract equations or programs that explain the data. OK, so what's the state of the art in symbolic regression? This is, at this point, just classical genetic programming. Now, there are fancy algorithms for program synthesis, as we all know. But in this setting, researchers have found that evolutionary algorithms really scale very well. And so they have stuck with that. So what that looks like is that you are representing these expressions that appear in the equations as these syntax trees. And then you're performing all sorts of operations on them, all sorts of mutations. And then you are matching with the truth, right? And you are seeing, and you're optimizing, trying to get an expression that matches the truth as well as possible. And this process has been scaled up quite well. There are packages that use distributed computing and scale on clusters. There is a strong user base. For example, in physics, there are lots of folks that are using these tools for all sorts of problems. And so here are some examples. In black hole analysis, so discovery of scaling relations for galaxies. So galaxy halo connections, sub-halo properties, et cetera, right? So these are real methods that are being used by physicists in real problems. And really, this is a fundamental question, finding expressions that match data that applies to really any natural science. OK, so now let's think about what are the potential challenges with evolutionary methods in this sort of setting of program discovery. Now, what can often end up happening is that because all of the operations that you're performing on programs are purely syntactic, a lot of the times you may end up lots and lots of expressions that are just basically of the same sort, right? So there is an exploration problem that you may face. So you get these islands, and yes, in some of these methods, so in particular this PySAR, this is a particular package for doing symbolic regression using evolution. So they do things like move programs from one island to another island, and do crossovers and so on. But there is this fundamental issue that ultimately you are working with these syntactic operations, and that's limiting. So the insight that I have to offer you is that LLMs can really help with increasing exploration, and that happens because LLMs they can be used for certain kinds of abstraction, and we are going to see what that means very soon. OK, so let us talk about that. This is a paper that's going to appear at NeurIPS 24, and the work was led by my amazing undergrad, Arya Graeli, and my grad student, Atharva Sehgal. And this is also with Miles Cranmer, who's a physicist, Omar Costierre is a research scientist at MIT, and I was there too. OK, so let's talk about what the notion of concept is over here. So let's look at these three curves over here. OK, and these come from very different settings. What's in common between them? Yeah. So they're all, power laws, basically, right? Now, if I look at this expression, it looks like a power law. And if I look like those graphs, it also looks like a power law. But, if I say that, if I start with this expression and turn it into this natural language sentence that says power law trend, I have basically performed a sort of abstraction. I have come up with this higher level notion that applies to a lot of concrete equations that have this form, right? And that's going to be the one important idea. And another idea is that, so suppose you have this sort of a high level concept, right? So let's say that this concept is created by a human physicist, or maybe you've used an LLM to come up with it. So if, for example, you know that there is this kind of concept that is useful for your equation discovery or program discovery, you are hopefully going to have an easier time, right? It's like somebody told you that look for this kind of program. And so the point is that these concepts can be used to direct the process of equation discovery. So in this particular case, you have this equation which looks fairly complex, and it shows up in the context of gravity waves. So if you were just doing a search over the space of equations to discover this, you would probably have a fairly hard time. But if you have some of these observations that maybe you have made in previous programs, previously generated equations, previous research papers, or maybe you have just imagined it up, then you will presumably have an easier time discovering this expression. And so really the idea is that you are using these sorts of concepts in guiding the search for programs. So then these are the ideas that really drive this process that I'm about to describe. So there are three parts of this. So there's the part of hypothesis evolution. So the hypotheses here are just programs. So you're evolving the programs, but you are doing it, as mentioned, in a concept-directed way. And then there's the process of discovering new concepts, and there's the process of evolution even in the space of concepts. So there's a hierarchical sort of thing going on. You have evolution at the level of concepts as well as the programs or hypotheses. Okay, so this is what the program evolution looks like. You have these two pieces. So one part is just standard symbolic evolution. This is what we have always had in genetic programming. And then the other part is the other possibility. So the algorithm has the choice of doing the standard symbolic thing or this LLM-guided evolution. And so this LLM-guided evolution is conditioned on this concept library that is a bunch of natural language strings that you have discovered. And then, so as you're doing this evolution, you're also, naturally, you have a fitness function which you're using to find the best hypotheses. So what does that look like more concretely? So if you look at the sort of traditional setting of evolutionary algorithms, so you're starting with an initialization, and then you have this program population. You're evaluating those programs. You're finding the best program, and then you're doing mutation or crossover, or maybe there are some other symbolic operations like simplification and so on, right? And then this process is repeated over time. So now what we are saying is that all of these evolutionary steps can also include the option of using something LLM-guided. So the initialization can be done by an LLM. So you just start with a high-level prompt where you describe what you're trying to do and maybe some background information. And then you initialize. You spit out a bunch of initial programs. And then LLM mutation and LLM crossover is also like that. For example, for mutation or for crossover, now what you would do is that you'd be using the LLM. So if you think of the traditional crossover, it would be just you're randomly choosing a node to remove and randomly choosing something to add and so on. But the LLM-guided version would just be using a prompt like this where you are giving a bunch of these expressions, and then you're asking the LLM to cross over these expressions. Right? So that's the idea. And you have a choice between either of these two strategies. And naturally, the LLM version is conditioned on the concept library as well. OK.
Right.
Yeah.
So where's the concept playing a role in the mutation or the crossover?
Where's the what playing a role?
The concept.
The concept is part of the prompt as well. So for example, when you are doing mutation or crossover, that's where you are using the LLM's knowledge to guide the search process, right? Because the mutation and crossover are what the search is based on. And that is the point where you are using concepts that, hey, here are some of the ideas that I've found valuable in high-performing programs until this point.
Can you give us an example about how that actually works concretely?
Right. So let me. Yeah, I have an example. So let's see. So let's just talk about this. So for example, here, a particular program or equation that you may have found is this, right? So now you're using the LLM abstraction to basically get this sort of a high-level concept, which is there is exponential growth or decay. Now the point is that as the evolution process is ongoing, you are doing this sort of thing at many steps. So you're discovering the concepts that tend to appear in high-performing programs. And so does that make sense?
I just don't see it. Then, well, keep going.
OK, let me just just go through the whole algorithm, and then we can come back to this. Okay, so then the first thing that I talked about is the hypothesis evolution. And so for now, let's assume that there is a concept, a set of concepts that you have discovered, okay? And you are doing the mutation and crossover conditioned on those concepts. So then the next step is doing this concept abstraction. So now suppose that you have a bunch of these programs, and so you are selecting the highly performant programs because you have a fitness function, you can select the best programs out of the pool. And then you're asking the LLM to do this sort of abstraction. You are essentially summarizing the trends that are showing up in the high-performing programs. And so in this case, it would be that, so if I start with this program, an example thing that might show up is that you are doing, there is exponential growth or decay, right? So this is a concept that then gets added to the library. And then once you have that, then we also have this sort of evolution in the concept space. But these are, of course, all natural language expressions. So how do you do evolution? Well, the LLM can do that for you. So you can ask the LLM to, for example, combine these two concepts, exponential growth decay and depends on temperature. So the LLM has all this wealth of prior knowledge. And with that, it might be able to discover that, this is a Boltzmann distribution. And then this then gets added to the concept library. So there is this iterative process, and it's completely open-ended. You discover concepts. You use the concepts to guide the discovery of programs, and so on and so forth, right? Which leads to new concepts. Yeah.
So, thank you. How is that not just a compositional prompt for a retrieval rather than evolution?
So you are doing, so when you have this...
the concept of evolution that you mentioned.
Right. So you have the standard evolution process happening as well, and then periodically you are doing this sort of an LLM-guided mutation and crossover as well, right? So what that means is that you are really using this sort of LLM-guided steps as a sort of regularizer for the traditional symbolic evolution where you're just doing random search essentially in the space of programs.
So it seems like what you're calling LLM evolution is simply retrieval, or some kind of compositional prompt and then retrieval from the LLM, right?
I mean, it's not quite retrieval from a database, right? So it's generated by the LLM, right? So it's whether or not you call generation from the LLM retrieval or so because it is happening in a step-by-step way, and it's informing this kind of a symbolic traditional evolution process. So that's why we called it, LLM-guided crossover, evolution. But yeah, if you want to call it, just generation step,
awesome.
That's fine.
Maybe also clarify the symbolic evolution part. So I don't see that in this example.
So so the symbolic evolution just happens for certain steps, and then you do some, one LLM-guided evolution step just because, the LLM is expensive, and so we are kind of mixing the two things, right? So the appeal is that the problem with this traditional symbolic approach is that it can go completely, off the rails. So this LLM-guided steps, they offer a sort of regularization. You are using the LLM's knowledge to kind of direct the process a bit more. But you can choose a trade-off between these two different strategies. For example, you can do it, 50-50, or you can do it 1% of the time, and so on. Yeah.
Perhaps if I ask a question too, that might be. So if I'm like a very standard genetic algorithm, symbolic regression, genetic programming algorithm interacting with an LLM, what people do is they say, well, I have this population of, I might ask the LLM to give me an initial population of candidate solutions that are in program code form, and then I might run them somewhere and select the best, and then I go back to the language model and I say, well, here's two, can you give me one that's a crossover between the two? And what I would normally do in an evolutionary algorithm, if I'm asking you this, well, I would normally do that very randomly, the crossover, but because the language model has all these patterns of code in the past, it's more like it's going to give me a biased mutation, but it's a mutation that's biased by the knowledge of code patterns.
Right.
But so now to help me get to the step where there's language involved, where I have this cool idea that I'm going to describe some of my the system identification problem I have by some of the concepts relational concepts that I need, like depends on a temperature or has exponential growth. Where does the language part come in? Am I going to take my code and then convert it to a language description, or how is the language description and the search and language space going to get converted to the code space?
So the generation of the process. So let me just go back to this one. So here, what you're doing is that the prompt that you're using for doing this sort of crossover, that includes these high-level concepts that you have discovered, and those are just language, right? So that's the appeal of LLMs. Yeah.
How do you remove concepts? So you include finite number of concepts in the prompt, but the library itself grows, or
The library grows, and then you select some subset of them. You sample a set of concepts from the library, and you put that in the prompt.
like uniformly, or do you ever remove something from the library?
Yeah. So there are some heuristic lower level engineering strategies which are dependent on the problem. But yeah. So of course there is this issue of you cannot grow forever. So you would need a notion of how useful the concept is, and there are proxies for that, right? So how frequently have you used a certain concept in doing useful things? Because the point is that there is ultimately a reality check. Programs that you're generating can be evaluated using the fitness function, and you can see whether certain concepts have proved useful or not, right? So there is a backward information flow and so you can use that to filter some of the concepts out of your library. Does that make sense?
Yes, I guess I would need to read the paper to understand.
Okay, sounds good. All right. So then, just to give you a sense of what this looked like visually, so after this first phase of generating new programs, you may have these islands of expressions, and then when you're abstracting them in language, you might get information like, okay, so some of these programs exhibit linear trends, some of these exhibit exponential trends, sinusoidal trends, power law trends, and so on. And then the concepts can expose these sorts of unknown space of programs. And so, for example, the sinusoidal trends might lead to some of these other trigonometric expressions that you didn't know before. And then also, from the sinusoidal trends, using this sort of crossover, you might get, trigonometric trends, which is something more general. And the point is that concepts can expose new concepts, and concepts can expose new programs as well. Yeah.
Is there ever a case where a natural language concept gets mapped to two distinct islands, like the same?
Yeah, totally, it could. Yeah, I mean, this is all kind of fuzzy, right? So it's not like this notion of islands is explicit. This is more just sort of an intuition as to what is going on. It's not like you are, clustering those programs, in very explicit buckets.
But does the LLM understand how to draw the sort of decision boundaries, or like come out of those loopholes in some sense? Yeah.
Probably. It's not like we have explicit guarantees that the LLM is going to pick some new concept or pick some new island, right? We don't even know what an island is, formally. It's more like just an intuitive idea that the space of programs can be sort of clustered semantically into a bunch of buckets.
So if you want to form this concept library, one thing you can do is you can kind of just randomly use concepts and see how effective they are and put the effective ones in. But it would seem that it would be even better if you could understand what the code was doing and then pick a concept related to either the domain or related to some deficiency or strength of the code itself.
Absolutely. So there is a lot to be done on, for example, bringing in some sort of program analysis into the picture. So it's really, a very open-ended space at this point.
Because so many times you have genetic algorithms, and the problem is you can't bring domain knowledge in. The only way you can bring domain knowledge in is you pick your representation, right? So in the case of doing something like symbolic regression, I'm just picking variables in the space that I've already dependent, and I have a sort of free space for the model structure when I do this. But when I, if I have some very complicated system that I know the variables, I know some relationships between the variables, I can put those as concepts in.
Yeah.
It all drifts into my system with a bias.
Right, for sure.
It's noisy because you don't know what unless you put the right prompt information with the right code, it's going to be noisy for.
Right.
So you showed us these nice examples of graphs of functions, and then we all could see there was a power law or exponential or something. Can the language model do the same thing? Like if you show a picture, does it? Yeah,
that's a good thought. So we have thought about that. We haven't done that yet. So this is all very new stuff, but that is an interesting question. That if you have vision language models in the picture, what can you do? So I'll show you some stuff with vision later, but it's going to be much simpler than any of this. Sumit?
So do you intend to also fine-tune the large language models?
Eventually, yes. Yeah, so again, this is all very new stuff. But in principle, yes, you can do fine-tuning of the LLM.
Because the gameplay that you will play, that will get like this, will give you a lot of label data.
For sure.
Is it fair to say that abstraction through language is allowing you to jump around the semantic space of
Exactly. So that's the idea, that the abstraction allows you to jump to way far off points in the space than you could normally. And this is true for any abstraction, right? But language is very convenient because you can use LLMs without, so for example, in Dreamcoder, you have these amazing libraries which enable a lot of this as well, but then you have to, do the sort of substructure extraction and all that, but LLMs allow you to do an abstraction without any problem.
I mean, I can anticipate a little bit of trouble with successful concepts in practice being somewhat bespoke to the problems you've solved.
Yes, and in fact, sometimes they are also bogus because LLMs just come up with junk, but that's something to fix. So I think there's a lot to be done on factuality verification of the concepts and programs. Let me come to that in a second. Yes?
So where is sketching in this algorithm?
What sketching?
The use of sketch. So this is one way for the user to also provide insights into.
Oh, I see. So you can have hints as part of the prompt, right? So that's the joy of LLMs, that you can start with information, all sorts of background information. So I'll give you some numbers on what happens if you have some hints from the user about what kind of programs are interesting. Now, those things are also harder to evaluate, so it's going to be a bit more anecdata than science. OK. So then in terms of the overall performance, we evaluated this on this Feynman equations data set, where the goal is to discover all the equations from the Feynman lectures in physics. This was from Max Tegmark. And we found, at least with the compute that we had, quite a few more equations than the existing methods. Now, of course, there is a little caveat here. With LLMs, you don't know, if there is contamination. But we did quite a bit of analysis that suggests that the way in which these programs were derived, because it's not like you are just spitting out the equation, the program in one step. You are doing this kind of evolutionary path. So it's the process seemed to find a pretty convoluted path to many of these programs, which suggests that it's not just a matter of memorization. But the paper has more details. So then what we found is that using these really large models like GPT 3.5, it really it helped. But even with just local small language models, 8 billion parameters, you still got better performance than this purely symbolic approach. So this PySAR is the baseline, and this is LaSR, and this P is the probability that you are using the LLM-guided step, right? So as you see that as you increase this P, you discover a few more. Now, of course, these are all sort of small numbers, but we do think that the capabilities go up as you use the LLM more, at least from 1% to 10%, and when you also use these sort of bigger models.
This looks good. I wonder, what is the difference in compute between the different approaches, and is it a fair comparison?
It is a fair comparison, in my opinion. The paper has the numbers of how many steps. I've forgotten the exact numbers. So, but this was definitely in our mind. We didn't give them the same amount of same number of iterations. So because we are using LLMs, that incurs some costs. So we were mindful in these comparisons of of making sure that there was fairness in the compute.
Less steps to the LLM.
Yeah.
To make sure the compute is equal.
But you trained the LLM.
Yeah.
We didn't train the LLM. So
I know, but the LLM is pre-trained.
Sure, for sure. And by the way, this can only be done for the Llama version, because for GPT 3.5, who even knows what kind of compute is being used?
It's interesting that at inference time, they kept it equal. That's what I was asking.
Yeah.
It was a pretty expensive set of experiments, let me just say that. OK, so then what about human-provided hints? So it does help. And for the details about what these hints exactly were, you can look up the paper. So basically, it was the chapter of the the chapter heading in the Feynman lectures on physics. Not much more was provided. And that kind of information already substantially improved the capabilities. As you see here, this is the iterations, and this is the number of equations solved. And eventually, it seemed like they both caught up. So this yellow one is the one without hints, and this blue one is the one with hints. And then, as you see, that the one with hints is better because you are solving more equations more quickly. But then eventually, it seemed to mostly catch up. But this is also something that one can experiment more with, that if the hints are richer, maybe there's going to be a difference, or if the equations are more complicated.
It would be interesting to try it on like the benchmarks for symbolic regression.
Sure.
Synthesis, right?
Sure.
Because your particular benchmark here is from science, and you're giving it science concepts.
Right.
Like the other ones are either mathematically derived, or they're
right.
rule systems or something. So
right.
The question about whether the value of the hints and the concepts, you may have a nice sweet spot here between physics and physical concepts.
Right. Right. Okay, and then this is a concrete example. So we also found that the use of the LLM, it helps with finding more natural looking equations. So this is Coulomb's law for electricity, electrical force. And so the way this experiment was set up is that you are starting with this ground truth equation. You are generating a bunch of data using that equation, and you are then adding some noise to it. So you have this noisy data set, then you're trying to extract back the equation that produced this data. So this is the genetic algorithm. As you see, it's pretty nasty, but it can be simplified. So if you do 10 steps of simplification, it will end up reducing to the ground truth, but it is more unwieldy. But by contrast, the solution that we got with LaSR was a lot more clean, and it reduced to the ground truth after only 4 steps. Now again, this is anecdotal, but there does seem to be this effect that you are getting more natural equations, and in fact, we found that smaller models tend to synthesize simpler equations. But this is something we need to investigate more. Rupak?
Yeah. So let me be the devil's advocate.
Yeah.
So for classical theorems and classical results where you have this kind of closed form solution, this is all very good. But a lot of physics is where the law is given implicitly as a solution of a dynamical system.
Right.
Navier-Stokes equation. Now the closed form solution of these we don't even know, right? We can generate data by numerically integrating.
Okay. Can I answer this question in just 2 minutes? Maybe I'll show you one more thing, and then we can get back to that. I think that's a fantastic question. Okay. So what were some of the concepts like? These concepts were fairly weird in some cases. So here I'm showing some of the weird ones. Actually, no. So these are actually reasonable because it is talking about power functions and so symmetry or regularity, division, multiplication, trigonometric functions, and so on. So these are reasonable kinds of things to see in the expressions. But naturally, there is no guarantee of factuality or correctness. That's where I think there is room for doing some sort of verification or fact-checking. And also, sometimes you can get weird concepts that are just misleading. So in the longer run, our view is that these concepts are also a mechanism for interpretability, in the sense that you're not just getting programs, you're also getting these explanations for why these programs are reasonable. Okay, so now to come back to Rupak's question. So can we do new discoveries using this kind of method? So there are 2 parts of this. So one is that there are situations where the underlying expression is extremely difficult and unwieldy. And the other case is one where maybe there is a simple law, but it's just that we don't know that. It's not known to humanity at this point. So we haven't really done sort of a full-fledged scientific application, but we have done a smaller version of that, of the second case, which is the problem of finding LLM scaling laws. And so we actually found a new scaling law for LLMs using this method. And so just to set the stage for that, so this a couple of years back, there was this paper from DeepMind, the Chinchilla paper, where they discovered the scaling law for LLMs. Basically, how does the performance of the LLM change as you increase the model size and the data size. And there is this scaling law that they posited. And this was done by essentially first they came up with this general form, and then they fit the parameters to data. And this data is basically you have a data set of problems, benchmarks, and then for each benchmark you are evaluating the LLM, and you're looking at what kind of performance it got, and then you're trying to find a law that explains it, right? Based on the parameters of the LLM, how much data it was trained on, and what is the model size. Okay, so we did a thing like that. We just unleashed LaSR on this problem of finding scaling laws for LLMs. So we started with this benchmark of benchmarks called Big Bench. So here you have a bunch of different tasks. And for each of these tasks, you have some information about, so there is a notion of a score, which is a rank in this case. And you have information about the number of training steps and so on and so forth. So one other variable that was not there in the original Chinchilla paper is the number of shots. That is the number of examples that are being used while you are doing inference. In few-shot learning, there is a certain number of examples of how to solve the task that's provided. Now you're counting the number of shots. So we wanted to ask, is there a dependence on the number of examples you provide? And it turned out that LaSR came up with this equation where this number of shots it figured. There were, of course, other variables as well, but this variable just didn't appear in the Chinchilla one, right? And so then what we found is that it leads to this sort of interesting prediction that if you plot the number of training steps versus the output score, and higher is better, and you look at the number of shots, you get these different sort of graphs. And what is intriguing is that it seems like, according to this law, as you increase the number of training steps, you are going to get to the same sort of place, no matter how many shots you use, but there is this variation before that, right? And this is a fact that just doesn't seem to be known to the LLM scaling law community. And so this is an example of a new discovery of an equation that is not Navier-Stokes, but it's a simple form of a law that's discovered using symbolic regression. Yeah?
I think I might be misunderstanding the graph. Is this saying that for a fixed number of training steps, like 0.5 times 10 to the 6,
yeah,
that having more shots makes you do worse?
So if you have a fixed number of, n equals 1 is this one, right? So if you have a small number of training steps, you are still going to get to a pretty reasonable score, right? So if you have by contrast, like something like this, so where you have a higher number of shots, then you are going to find that you would need more number of training steps to get to approximately the same level.
And you normalize for how many steps it takes in the prompt. So the one n equals 1 and n equals 7 are 7 apart on your x-axis when they start, because you have more examples and more shots. Is that why?
Oh, is that what's happening?
Sorry, say that again. I didn't follow.
Is that right?
It sounds like one candidate hypothesis here is that that the minimum amount of training, like you're multiplying the amount of training that the model needs by the number of shots, because each example in its training data set has...
No. So the number of shots is during inference. So the number of shots is this. So maybe we can discuss this offline. Okay. Yeah, this will take a little bit of a conversation. Okay. So then what we found is that so if you take the scaling law and you combine it with the traditional Chinchilla scaling law, it tends to do even better. And this is a thing that was done manually, but this is an example of how you can combine this sort of automatic discovery with manual analysis to maybe get something better. And yeah, we can discuss if there are more questions about the exact conclusions, we can talk about that offline. Okay, so I don't know how much time I have. Okay, 10 minutes till 50 minutes. Okay, so in recent part, we have been also been interested in extending these ideas to the visual reasoning setting. And the point is that the equation discovery problems that I showed you, so there the data is not very high dimensional. But there are many settings where you want to actually operate on visual data. So this is an example from ecology. This is from this iNaturalist project that Pietro Perona and others at Caltech and their collaborators have. And so here they have all these crowdsourced data on various sorts of animals, pictures of various sorts of animals. So there is, it's really interesting because you have, for example, this picture of this lizard, and then there are folks that are having debates about what this thing is. Is this a Florida scrub lizard? No, somebody says it's more like a northern curly-tailed lizard, and so on and so forth, right? And then you also have data about locations so this is the metadata that is there in the images. And so you can use this kind of data to answer scientific questions like, okay, are certain kinds of lizards losing their habitats because of climate change or invasive species and whatnot? Okay, so I'm not going to talk about that whole problem. This is something that we have just started. But the longer-term ambition is to really do science over this kind of visual data from ecology, from astrophysics, and so on. So how does this connect to concrete stuff that I was talking about? So let's just talk about a very basic version of this, which is image classification. So I'm given a picture of, let's say, this adult bald eagle, and I want to identify whether or not it's there. So now one approach that has recently gotten traction is to use VLMs to solve these kinds of problems. And in fact, combinations of LLMs and VLMs are turning out to be quite useful. And there is a parallel between this and what we saw before, in the sense that one approach developed by Carl von Wrijk and his students is something like this. So you start with a question like this, so identify the adult bald eagle. So you ask an LLM to generate these sorts of descriptors or really concepts in the language that I mentioned earlier. So this could be, for example, bald eagles have large wings or large beak or white head and black body and so on, right? And so you're using an LLM to generate this kind of concepts, and then you're using that to ask. So now you're asking the VLM that, okay, is this the case that this picture that I have has these features, right? And so based on that, you are answering yes or no. Now, one interesting example of this is that, so this is a ship, a famous ship. Does anyone know what this is? Exactly. So this became known as the Ever Given. But that name gained popularity only after the VLM that we use, namely CLIP, was trained. And so, CLIP shouldn't know about, what Ever Given is, right? But if you use the LLM, so the LLM would be able to, use background information to say that, okay, it's a container ship, it's actually called Evergreen, it has stacked containers and stuff like this. So once you provide this sort of extra info, then the VLM would be able to discern that this is, in fact, the picture of Ever Given. So actually, this thing can be plugged into a program. So in fact, later work by von Wrijk et al. Have done that, where you can imagine writing a program using these sorts of descriptors, and then you can do Python code execution and so on as well. But the question that I'm interested in the context of this talk is, can I actually do evolution and synthesis to discover these sorts of descriptors, these sorts of concepts? And it turns out that that actually helps. I don't have the time to show you a lot of experimental results on this, but I'll just give you the high-level idea. So in prior work, the idea was that you are starting with a question, you are generating some concepts, and then you are throwing it to a VLM, and you are getting results, right? So this is a little bit of a context switch. So this is about, is it a donut or a beignet? A departure from ecology, but you get the picture that the LLM gives information like a donut is hole in center, glazed surface, desert, beignet is all these things, and that's it, right? But now, by contrast, so in the the work that we have been doing, you're actually discovering a library of concepts for each of these classes. So for example, beignet, right? What is the Bayesian-ness of a beignet, right? What is the essence of that in words? And this is something that can benefit from this sort of exploration as well. So specifically, you could imagine that you start with that sort of step, that what does a donut look like? What does a beignet look like? Okay, you have these descriptions, right? But then you actually use the VLM as a critic, right? In the sense that you use the VLM on the training examples and see where it is getting confused, for which attributes it is getting confused. Like, for example, maybe the real distinction between these two kinds of treats is that the beignet has a puffy texture and the donut has a circular shape, right? But this wasn't apparent in the first set of concepts that you got. But with this sort of iterative exploration, you are able to discover these new concepts as well, right? And so basically what is going on is that if you draw the parallel with the previous method, so there you are using the knowledge of the LLM, and you are combining that with the ground truth, the reality check of the scientific data. In this case, you are doing this sort of evolution using the LLM, and you are grounding that using feedback from the VLM. Namely, you are checking where the VLM is getting confused, which are the attributes, and so you are trying to discover more concepts that would disambiguate the decision between these two categories. And again, I won't be able to give you any results, but yeah, so this is the overall idea. So you have this kind of iterative concept library creation. You get those new concepts, you feed it back, and this process continues. And we find that this sort of iteration actually helps with classification accuracy substantially. OK, so now I want to just go high level. Is there any question about this last bit? It's sort of, yeah.
So the supervision for this is it like kind of donut and beignet specific? Or is it like you're kind of learning in general, like, oh, circular shapes are good for VLMs, so therefore when I need to detect tires?
No, it's for class specific. So so for each class you're discovering this library of concepts that correspond to that class. Yeah. OK, so now I want to go even higher level. So what are some of the open challenges in this area? To summarize, what did I do here? So I think that this sort of combination of concept abstraction and search with LLMs is I think, very interesting. LLMs provide a natural means of abstraction and also a natural means of guiding the search process. And there's a ton of stuff to do here. So some of the open challenges are, how do I do verification of hypotheses and concepts? Can I represent concepts in ways beyond natural language? So natural language is easy, but it's also not really as compositional as programs. So I would ideally like to have something like Dreamcoder as well, except directed by LLMs. And how to do that, that's a bit of an open question. Then scaling to larger search spaces and input dimensions, more ideas need to be there. And as mentioned, this is all in its infancy. I would love to have feedback from all of you and even collaborate if possible. So one other thing I wanted to say is that I'm really, as a long-term direction, intrigued by the connection between these sorts of empirical discovery using evolutionary algorithms and this other line of work on AI for math that I'm really excited about. So there's this emerging picture of solving mathematical problems that involves, you're trying to solve informal reasoning, and then what you do is that you formalize it using an ML model, and then you prove this sort of the formalization, a proof of the formal statement using another ML model, right? And the language of formal statements is Lean or Coq or any of these sort of formal proof-assistant frameworks. And this has turned out to be a really powerful way of doing math. So for example, alpha proof at DeepMind, which I've had the honor of playing a very tiny part in, is a great example of this. But there are also a lot of open source efforts that are using this broad idea. OK, so then we have some stuff here too. We have this LLM agent that does this kind of math reasoning, but I'm going to skip all of that. Let's just get to the punchline, which is that, could we somehow combine empirical reasoning and this sort of deductive mathematical reasoning? So could we, for example, imagine, lean being a language of expressions, and then, constructing hypotheses and concepts in lean from experimental data, but then you also have this sort of formal, deductive reasoning to essentially create deductive closures, come up with implications of what you have seen so far. And then, evolving these sorts of deduced hypotheses as well. So in the long run, we really want to get to these sorts of hard questions where, the math is also potentially very difficult. There may not be a closed form solution, but maybe you can combine your deductive reasoning, maybe other things like numerical simulations, and this kind of empirical discovery all together, right? And hopefully that is something that will help us with this sort of long-term goal of building AI with high performance at natural science research. Thank you.